Electric dipole. Let's try to make a nice diagram. X, Y, Z. We have at location A on the x-axis, at location I call that point B, we have a charge plus Q. On the other side, A from the origin on the x-axis, and I call that point capital A, we have minus Q, and you're being asked now to calculate the E field everywhere in space. Let us choose this point in space, which has as a location X, Y, and Z. And let's try to make a three-dimensional plot. So this is the X position of that point P. This is the Z position of that point P. Ooh, I hope that I can draw straight lines. It's not so bad. And this is the Y position of that point P. I hope you can see this as a box. And at the corner of the box here is that point P. And the vector from the origin to point P is this vector, and I call that vector R. And it is immediately obvious that R, the magnitude of R, equals the square root of x squared plus y squared plus z squared. Now I'm going to first calculate the electric field at P only due to point B. And then later we're going to add the electric field due to point A. I'm going to shift the entire coordinate system to point B. So I'm going to make a new coordinate system. I call this y prime. I call this x prime. And I call this z prime. This point is now not O, but this point is now point B, where the plus Q charge is. And here is now that point P. The distance between B and P is now this vector. I call this angle theta. And I will try to make a projection again so that you can see things. This is the x prime position. This is the z prime position. Let's call this angle phi. And so this is the y prime position of P. If this angle is theta, then of course this angle here is also theta. I want you to appreciate that x prime is x minus a, because we have moved up the origin only in the x direction, but that y prime is the same as y, and that z prime is the same as z. That has not changed. So for point P, the x prime position is x minus a, the y position is the same as y prime, and the z position is the same as z prime. What is the distance BP? Well, BP is the square root now of x prime squared, for which I can write down x minus a squared, plus I can write down y prime squared, but I might as well write down y squared, plus z prime squared, for which I might as well write z squared. What is the electric field E at location P only due to this plus Q charge at position B? We know that it is along the line BP pointing outwards in the direction BP. So I will try to put it in here. I will call it E of P. It's in the same direction as BP. The magnitude of it equals Q divided by 4 pi epsilon 0 times bp squared, namely the radius squared. And it is pointing outwards because this q is positive. Now I want to know what the x component, the y component, and the z component is of this vector. And now I need the help of these angles theta and these angles phi. It's now becoming a mathematical problem, no more physics. Ex, as you can confirm for yourself, is the magnitude of EP times the sine of theta times the cosine of phi. E of y equals E of p times the cosine of theta. That's very easy to see. Once you know what the magnitude EP is, if you want to know the projection in this direction, then all you have to do is multiply it by the cosine of theta. And E of z equals EP times the sine of theta times the sine of phi. Maybe I should have said here x prime. The component in the x prime direction. Okay. Now, what is cosine theta? By the way, the x prime direction, of course, is also the direction of x, so it's really absurd to call it x prime. It is the component of E in the x direction, so forget the prime. Cosine theta equals y prime divided by bp. Convince yourself of that. The sine of theta equals, now I need this length for the sine of theta. And this length here equals the square root of x prime squared plus z prime squared. And so the sine of theta equals the square of x prime squared plus z prime squared divided by bp. The cosine of phi equals x prime divided by that same square root, and the sine of phi equals z prime, again, divided by that same square root. And I really think you should check that very carefully. And when I substitute these cosines and sines in here, I find a very simple answer. I find that E of x equals this q divided by 4 pi epsilon 0 bp squared times x prime divided by bp. But remember, x prime equals x minus a. X prime equals x minus a. I find for E of y the same thing times y prime divided by bp. But remember, y prime equals y. And I find for E z the same thing times z prime divided by bp. But remember, z prime equals z. And so, for this one charge at location B, for that one alone, I find q divided by 4 pi epsilon 0, and now I'm going to get here all the rest. I get here x minus a unit vector in the x direction, plus y unit vector in the y direction, plus z times the unit vector in the k direction. And downstairs, I get x minus a squared plus y squared plus z squared to the power 3/2. That now is the complete contribution only from the charge at point B. You now have to add the part from point A, so you get a minus q divided by 4 pi epsilon 0. And you get exactly the same thing here, except that wherever you had a minus a, you now get a plus a. For obvious reasons. And so you have to add the two up, and you see immediately the answer that you were given in your book. Now, they want you to simplify this in the case that R is much larger than A. And this begins again to be mathematical manipulation, and we're using Taylor's expansion. Keep in mind that this vector is almost R. It's almost the vector R, because the vector R equals x times this, plus y times this, plus z times the unit vector in the z direction, except for this one here. So I'm going to rewrite this, and I forget now this term. Just forget that. I'm only interested in the geometry. So I get R minus a I to account for this. And downstairs, you can convince yourself that this is very close to r squared to the power 3/2, but not quite, because you have this term here. And so if I work that out, I get r squared minus 2ax to the power 3/2. Have I cheated? Yes, I have cheated a little bit. I have ignored a squared. Because notice when you square this, you get an a squared. But since r is much, much larger than a, I feel completely justified doing that. But I'm going one step further now. By the way, I only take this first term. Second term, you work out yourself. I'm going one step further. And I'm going to use something that perhaps you remember from last year, that if x equals much, much less than 1, that this quantity is approximately 1 plus n times x. And so I'm going to take the r square out of the brackets here, so I get r minus a times the unit vector in the x direction. Then I get an r cubed here, because don't forget there's this 3/2. And I get 1 minus 2ax divided by r squared to the power 3/2. And I know that this is much, much smaller than 1 when r is much, much larger than a. And so I can apply the same Taylor expansion that I have here. And so this now becomes r minus a I roof divided by r cubed. And then I have here upstairs 1 plus 3ax divided by r squared. And this is now where my Taylor expansion has come in. You will now have to add the term due to a, which is due to the charge at point capital A, which is going to be extremely similar. Don't forget that the charge was negative. So you put a negative sign there first, and then the signs of A will flip. So this will become a plus, and this will become a minus. What you do then is you're going to add those two terms up. So this is the geometry term only due to capital B. You add to it the geometry term only due to capital A, to the minus q charge. And a lot of terms, when you work this out, will vanish, but they will not all vanish. And so you'll find then that the final E vector, for the case that R equals much, much larger than A, you will find that that is approximately Q times 2A divided by 4 pi epsilon 0 R cubed. And then here you will get 3 r vector times x divided by r squared minus the unit vector in the x direction. That is the final result. The result can be slightly simplified if you want to, and you are being asked to simplify it. You are being asked to somehow manipulate this number to convert it into a dot product. If we leave this alone, and you are willing to spend the time, you can prove that the term here can also be written as 3 times r roof, that means the unit vector in the r direction, dotted with the unit vector in the x direction, this is a dot product, times the unit vector in the r direction minus I. It took me a few minutes to convince me that this and this is the same. And this whole term then, of course, appears here. And so what you see is that both this term and this term fall off as 1 over r cubed. That may not be so obvious from this, but it is obvious once you have massaged it in this form. It's proportional to 1 over r cubed. And that now is very characteristic for a dipole. If it were a monopole, if I had only one charge, we know, we have already done it today, then the electric field falls off as 1 over r squared. But when you have a dipole, the positive charge and the negative charge, in a way, try to cancel each other. The positive charge at point B is having an electric field vector pointing away from point P, from B to P. But the negative charge at point A is introducing an E vector which is pointing towards point A. And so in a way they are almost trying to cancel each other, but not quite. And that's why the dependence becomes 1 over r cubed. So it's much more sensitive to how far you are away. It falls off much faster. When you're very, very far away, you can sort of see that the vector due to B, E, due to that point B, and that the vector due to point A are beginning to almost cancel each other. Because if it's very, very far away, the fact that A and B are not exactly at the same location almost doesn't matter anymore. All right, I will also want to show you why this is minus unit vector in the x direction. If we put the charge either on the y-axis or on the z-axis, then this term equals 0. Convince yourself that both on the y and the z-axis, the dot product between the unit vector in the r and the unit vector in the x direction must be 0. Because y direction and z direction are perpendicular to x. So it's going to be 0. Another way of putting it is when x equals 0, you can also see here that this term is 0. So you only end up with this term. So let's take that situation that we have now here the x-axis, here the y-axis, and that we have here a charge plus q at location B, and here minus q at location A. Then we know that the electric field lines run like so. And no matter where you are on the y-axis, that means as x equals 0, there will always be an E vector pointing in the minus x direction. Always. And that is exactly what you see here. If I have the right... Oh, sorry, my sheet fell all the way on the floor, but it was in the minus I direction, in the unit vector x direction. That's exactly what you see. It's very easy to imagine. Okay, we've come to the end. I have a minute and a half left. I will watch the tape to correct possible slips of the tongue and slips of the pen. There are always some, but I have enough time to correct them, I hope. So don't go away yet. Over, but not yet out. And then at the dipole problem, I said if you put a charge on the y or the z axis, Of course, I didn't mean putting a charge there. The charge is always on the x-axis, plus A and minus A. What I meant is if you measure the electric field on the y and the z-axis. And so that's what I did here in this drawing. You are looking here at the electric field, and you will see that then the electric field is always in the minus x direction.